Welcome to the Depth Dive. Today we're diving into the process that builds pretty much the entire cosmos, astrophysical accretion.
hmm It's this universal gravitational thing, gathering gas and dust.
Shaping galaxies, stars, planets, usually involving one of those spinning, flattened disks of material.
Right, it's like the foundational law of cosmic construction.
Mhm.
But, well, our source material today highlights a discovery that's causing a bit of a cosmic identity crisis.
Ah,
Yeah, a free-floating object, planetary mass, it's breaking all the rules we thought we knew about how things grow.
okay, so who's the troublemaker?
This object is Chak 1107-7626. It's about 620 light years away.
And astronomers caught it doing something unexpected.
Unexpected is putting it mildly. They caught it in an absolutely unprecedented accretion burst. It was basically caught gobbling gas and dust at a, frankly, shocking rate.
How shocking are we talking?
We're talking 6 billion metric tons of material per second.
Wow, 6 billion tons a second.
Yep. And just to give you some context, this single event, it's the most powerful accretion episode ever seen for an object this small, this planetary mass size,
So you've got this lonely world floating out there by itself.
acting exactly like a newborn star. It's wild.
This really does sound like more than just a weird data point. It feels like it could force scientists to rethink that line between a star and a planet.
Precisely. That fundamental boundary. So maybe before we get into the nitty-gritty of this anomaly, we should quickly set this stage.
Good idea. Remind ourselves how the cosmos is supposed to build things.
Yeah.
Especially the difference between stars and planets.
Okay. So when we talk about star formation, it usually starts with a giant molecular cloud, right? Huge cloud of gas and dust.
And it collapses under its own gravity.
Exactly. And as it collapses, it starts spinning faster. That's the conservation of angular momentum kicking in.
Which flattens everything out into that classic spinning accretion disk.
Around a hot core in the middle, that's your protostar.
And this leads to the T-Tauri star phase.
That's it. It can last millions of years. And it's usually characterized by, let's say, managed growth. Relatively smooth.
How so?
Well, the protostar is feeding on hot gas from the inner part of the disk. But crucially, it also drives these incredibly powerful jets, bipolar jets, shooting out from the poles.
Ah, right. The jets that help it shed momentum.
Exactly. They carry away that excess angular momentum. It allows the star to keep pulling in material without spinning itself into oblivion.
So star formation, while it sounds messy, it's got this built-in regulation mechanism. It's gravitationally dominated, manages its own spin problem.
Correct. Relatively straightforward mechanism-wise compared to planets.
Ah, okay. Because building planets inside that same disk, that's where things get tricky, isn't it?
Oh yeah, big time. You start small with microscopic dust grains. They stick together, maybe through weak forces like van der Waals forces. Little clumps form.
But then you hit that infamous roadblock, the meter-size barrier.
The bane of planet formation models for years. This is the real hurdle. Once these clumps grow to, say, centimeter or meter size, problems start.
What kind of problems?
Well, they start feeling the gas in the disk much more strongly. This causes them to drift really fast inwards towards the star.
Spiraling towards destruction.
Pretty much. And if they collide with other bodies of similar size at those speeds, the collisions are often catastrophic. They shatter instead of growing.
So it's like the universe is actively preventing things from getting bigger at that stage.
It makes it incredibly difficult. Growing past that meter size without getting destroyed or lost into the star, it requires special circumstances.
Like, what are the ways around it?
Well, modern ideas involve things like the streaming instability, where solids and gas interact to create dense clumps locally, or pebble accretion, where larger bodies can sweep up smaller, slower drifting pebbles more gently.
So you need these specific, maybe less common mechanisms to get over the hump.
Right. And that difficulty, that whole struggle, really highlights why this Che 1107 object is so bizarre.
Because it seems to be bypassing all that struggle.
Exactly. We're looking at something that should be battling these destructive forces, but instead we caught it in the act of rapidly, successfully packing on mass, almost like an unimpeded protostar.
Okay, let's zoom in on the anomaly itself then. Chess 1017-7626. Give us the stats on this thing.
Sure. So its classification is a bit fuzzy, free-floating planetary mass object, rogue planet, maybe sub-brown dwarf. They all kind of fit.
And the mass.
About 5 to 10 times the mass of Jupiter. So hefty for a planet, but way too small to be a star or even a proper brown dwarf.
And crucially, it's young.
Incredibly young, only 1 to 2 million years old. It's basically still in its cosmic nursery, an infant world.
And we saw this growth spurt thanks to some heavy hitters, instrument-wise, ESO's VLT and JWST.
That's right, the Very Large Telescope and the James Webb Space Telescope working together. They caught this monumental event.
So what exactly did they see during this burst?
Well, they measured that peak accretion rate, the 6 billion tons per second. But what makes it a burst is the timing.
Ah, the change.
Yeah, this peak rate was measured in late 2025. And it was roughly 8 times faster than the rate they'd measured just a few months before that.
8 times faster in just months. That's a huge jump.
It is. And there's even a hint from older data back in 2016 that suggests maybe a similar outburst happened then too. So these might be recurring events.
Okay, the rate is staggering, the burst nature is very star-like, but here's what's nagging me. 5 to 10 Jupiter masses. That's not nearly enough mass to ignite deuterium fusion, right? That's the usual cutoff for brown dwarfs.
Correct. Nowhere near the 13 Jupiter masses needed.
So how is something that small generating the kind of powerful magnetic field you'd need to funnel material onto its surface like that? Magnetic channeling is a T2 Tauri star thing, isn't it? Not for a little rogue planet.
And that is the absolute core of the paradox here. It's why this observation is potentially game-changing. The star-like behaviors they saw, they seem definitive, even though they shouldn't be there.
Okay, lay them out for us. What were the star-like signs?
Okay, first, as you suspected, the mass infall is being channeled by a magnetic field. That magnetically driven accretion is happening.
How do they know?
The spectral analysis. They saw hydrogen emission lines with profiles characteristic of material being forced down magnetic field lines and basically slamming onto the object's surface at high speed.
Wow. So this little sub-brown dwarf is lighting up its magnetic poles like a supercharged baby Jupiter, using magnetism to feed itself.
That's a great way to put it. Second, the way it brightened so abruptly and dramatically. It looked just like something called an XOR burst.
An XOR burst, sir.
These sudden, intense, accelerated accretion events previously only seen in, you guessed it, young stars, never on something this low mass.
Huh. Okay, magnetic funneling, star-like burst behavior.
Yep.
What else? Was there chemical evidence, too?
Ah, yes. This might be the clincher for some water vapor
Water vapor.
in the surrounding disk. But here's the key. It was detected only while the accretion burst was actually happening.
So the burst itself changed the chemistry of the disk.
It seems so. This kind of chemical transformation directly linked to the intensity of the accretion. Again, observed in protostars, never before in anything remotely planet-sized.
Okay. Let's pause and think about what this means, for the listener, for how we categorize things out there. Mass-wise, CHA 1107 is definitely in the planet category, below that 13 Jupiter mass fusion limit.
Comfortably below it, yes.
But behavior-wise, it's acting like a protostar. So which label matters more, the weight or the way it acts?
Well, this object really pushes us towards thinking the formation process might be the more fundamental classifier, maybe more than just the final mass it settles at.
Meaning?
Meaning if an object forms directly from the gravitational collapse of a gas cloud, like a star does, even if it ends up being really low mass like this one.
It still uses the same playbook, the same dynamic processes.
It certainly looks that way, including these, violent magnetic funnels and accretion bursts. It seems the mechanism is tied to the how of formation, not just the how much.
That has big implications for the whole rogue planet mystery, doesn't it?
Absolutely, because these lonely worlds are everywhere, trillions of them estimated in the galaxy.
But the big question was always, are they failed stars or are they ejected planets?
Right. Are these sub-brown dwarfs that formed alone from collapsing gas, just like the lowest mass stars? Or are they giant planets that formed around a star and then got violently kicked out of their home system?
And this observation seems to favor one of those.
It strongly favors the isolated formation idea, the sub-brown dwarf hypothesis.
Why?
Think about it. If Chan 1107 had formed like Jupiter and then been violently ejected, that ejection event is incredibly energetic. It would almost certainly have ripped away its primordial accretion disk.
Ah, so the fact that it has an actively feeding disk.
And not just any disk, but one where it's undergoing this highly structured, magnetically channeled star-like accretion that strongly implies it was born alone from its own collapsing cloudlet. It wasn't booted out.
Okay. Now, for the sake of covering all the angles in the source material, we should mention that this standard gravitational model isn't the only way some people are interpreting this rapid magnetic growth.
That's true. We need to acknowledge the electric universe perspective. which, it's important to state, operates outside the scientific consensus.
Right. They look at the same data very differently.
They do. For them, this observation is seen as, well, strong evidence for their models. They propose that magnetism and electrical currents are the primary drivers of celestial formation, not just secondary effects of gravity.
So how do they explain CHA 1107's burst?
They point to the 6 billion ton per second rate and the magnetic channeling. They argue that's an impossibly rapid rate for gravity alone to manage efficiently.
And the magnetism.
They see the magnetic channeling not as the object's own field guiding gravitational infall, but as evidence of a larger scale electromagnetic process, maybe like a Z-pinch effect along galactic electric currents, actively pulling the material in.
So for them, it's less about gravity and more about electromagnetism driving the whole show.
Essentially, yes. It's a fundamentally different interpretation of the forces at play, an important alternative viewpoint to note from the sources.
Okay. But bringing it back to the conventional model, let's put that accretion rate, 6 billion tons per second, back into perspective. It sounds enormous to us.
But cosmically, it's actually not that much mass accumulating over time.
Right. If you think about how much mass you need to actually become a star and ignite fusion, this rate, even though it's a record burst for this size object, isn't going to get it there quickly.
Not at all. Even if it kept up that peak rate constantly, which it clearly doesn't, it's a burst.
Yeah.
It would still take over 11 million years just to gain the mass equivalent to one Jupiter.
And hundreds of millions of years, maybe more, to even get close to the mass needed for true stellar ignition.
Exactly. So the real significance here isn't that this object is suddenly going to become a star because of this burst. It's about the mechanism.
The fact that it can behave like a star during its formation, even at this low mass.
Precisely. It confirms that the late stages of formation, even for these planetary mass objects, aren't necessarily slow and gentle. They can be dynamic, violent, and involve these star-like accretion processes.
So this lonely world, CHA 1107 7626, it really does shift our picture. It shows that these isolated planetary mass objects aren't just, cold, boring castaways.
Not at all. They can be exciting, chaotic, dynamic places in their own right. And it seems they might form using the same dramatic toolkit as the stars they sometimes end up orbiting. It suggests maybe a universal mechanism behind these accretion bursts that works across the whole mass spectrum.
And finding more of these must be tough, given how faint and isolated they are.
Extremely tough, which is why this discovery really underscores the need for the next generation of telescopes, especially the extremely large telescope, the ELT.
Its light-gathering power will be key.
Absolutely crucial for hunting down a larger population of these lone worlds, studying them, and figuring out just how common this kind of star-like activity actually is among them.
Okay, so we're left with this really fascinating cosmic identity crisis. If an isolated object, barely heavier than Jupiter, can mimic the intense magnetically driven growth spurts of a baby star, what other cosmic rules are we maybe about to see bent or even broken?
Especially as we start finding more of these trillions of rogue worlds thought to be drifting through our galaxy.
Yeah.
What other secrets are they holding?
Definitely something to think about until our next deep dive.